Chapter 9. Okay. If these three balloons are the same size, what is the bond angle between the red one and the green one? Well, it looks like 120. If the additional air is pumped into the blue balloon so that it gets larger, what happens to the bond angle between the green balloon and the red balloon? It gets smaller, right? Because the blue balloon is taking up more space. What aspect of valence shell electron pair repulsion is being illustrated by part B? The fact that unbonded electrons take up more space than bonded pairs, right? So lone pairs push harder, right, in terms of repulsivity than the bonded pairs do. So the bond angle gets smaller. For each molecule, A through F indicate how many different electron domain geometries are consistent with the molecular geometry shown. Okay, so in this chapter we talk about the geometry of the molecule, right? In this case, if you have a linear molecule, that's the relationship of the bonded pairs. And then we talk about the geometry of electron domains, right? All the electron pairs, the bonded pairs and the lone pairs. So if this were just a two bonded pair, no lone pair situation, we'd have a linear relationship. If it were a trigonal bipyramidal geometry, where we've got three lone pairs, 120 to each other, driving the bonded pairs 180 to each other, this is another situation where you'd have a linear geometry with a planar trigonal geometry of the electron domains. So octahedral geometry of the electron domains, right? This is when we have T-shape. All right, so those lone pairs are located in orbitals, right? So we talk about the geometry of the electron domains. So again, octahedral here. Octahedral. Another word for octahedral is square bipyramidal. Octahedral, right? So this would, the geometry of this molecule would be called square pyramidal, but it's square pyramidal because of that lone pair on the bottom, right? So this is octahedral geometry of all the electron domains. X-shape or square planar is an example of octahedral geometry of all the electron domains, right? The lone pairs driving the bonded pairs 90 degrees to each other. All right, with F, we have four bonded pairs and one lone pair, and we have a trigonal bipyramidal geometry of all the electron pairs. The only thing I'll say is when you have four bonded pairs and one lone pair, it's more like this, as far as my eye can see. It's more what we call a seesaw shape, right? The geometry between the bonded atoms is called seesaw. But overall, right, if we're looking at all the domains, right, plus the one unbonded pair, we have a trigonal bipyramidal geometry of all the electron pairs, or all the electron domains. So that's the difference, right? We talk about geometry, right, the relationships of the atoms to each other, and then we talk about the geometry of all the domains, which determines what the geometry of the molecule is going to look like. All right, so we have this molecule, difluoromethane. Based on the structure, how many electron domains surround the carbon atom in the molecule? All right, so this is four bonded pair, no lone pair, so this is going to be a tetrahedral geometry of the electron domains. Would this molecule have a non-zero dipole moment? Yeah, the way this is, the chlorines, because they're more electronegative than the hydrogens, would pull electrons towards the fluorine side, and that would create a dipole moment. If the molecule is polar, in which direction does the vector point? Well, it points towards the fluorines. Fluorine's more electronegative, and it's drawing electrons in that direction. So the negative side of this molecule is on the fluorine side, and the positive side of the molecule is on the hydrogen side. All right, with number 8, we have a relatively big molecule with multiple centers. So there is no overall geometry to this molecule. There's just geometries around the different centers. So we have 1, 2, 3, 4, 5, 6 central carbons, and each of these represents a center. So each of them would be hybridized according to what kind of bonding scheme they have around each of the carbons. So hybridization, right? To remind ourselves, right? Carbon has a electron configuration where we have to account for 6 electrons. So there's the core electrons in the 1s, and there's the valence electrons. All right. So in order to bond, we have to hybridize these orbitals in preparation for bonding. And the way this works is you promote an electron from the 2s, and then you mix the s shape with 1, 2, or 3 of the p shapes to make sp or sp2 or sp3 hybrids. So making an sp hybrid, I'd only mix one of the p's with the s, and I'd have 2 new shaped orbitals, right? One half s, one half p, and I'd have 2 bonding positions with those sp, sigma bonding, and I'd have 2 unhybridized p left over. All right, so these would be the sp hybrids, right? And, p is a dumbbell shape and s is a sphere shape, so when you mix them together, you get sp hybrids. So they're half filled, so they're ready for overlapping, and we have the unhybridized p, coming out of the plane here in the x and the y orientation. So we'll pretend the sp hybrids are in the z orientation, and that'd be sp hybridization for carbon, mixing one of the p's with an s. If I'm doing sp2 hybridization, I'm mixing 2 of the p's with the s, and I get 3 equivalent hybrids, right, that are 1 part s and 2 parts p. All right, so with this, you end up with 3 sp2 hybrids, right, and they align themselves 120 to each other with the unhybridized p sticking up out of the plane. So this is sp2 hybridization. If you're doing sp3 hybridization, you're mixing all of the p's with the s, so we end up with 4 hybrids, and each of these is in preparation for bonding. So when we have a tetrahedral geometry, right, a 109.5 degree bond angle, this is when we have sp3 hybridization. We need 3 half-filled hybrids in order for overlapping to form sigma bonds. So just to kind of go back over it, you promote the electron, you mix one of the p's with the s, we get 2 sp hybrids. This is when I have a linear geometry, a 180 degree bond angle. 2 unhybridized p's left over. With sp2 hybridization, I mix 3 of the p's and I get 3 equivalent hybrids, right? 3 sp2 hybrids. So that's important to understand, right? I mean, the number of hybrids you get is based on how many orbitals, atomic orbitals you're mixing. So if I mix an s with 2 p's, they get 3 hybrids. 120 degree bond angles between the hybrids. This would be for planar trigonal geometry. And if I mix all 3 of the p's, right, all the p's are gone. All 3 p's have been mixed with the s. I get 4 equivalent hybrids. Now look at the energies, right? If I was trying to show this, right, the energies are different than either the s or the p's that they're made from, right? It's a new energy shape. So again, when we want 4 bonding positions for bonding around the carbon, right, 4 sigma bonds, we have to sp3 hybridize. We have to hybridize all 3 of the p's. So with this molecule, right, I'm looking at the number 1 carbon. It'd be a planar trigonal geometry around the carbon. So it'd be sp2 hybridization. Around the second carbon, it would be a planar trigonal geometry, right? 3 sigma bonds and a pi bond. So there would be sp2 hybridization. All right, so planar trigonal geometry, sp2 hybridization. Four bonded pairs, no double bonds. That's going to be a tetrahedral geometry around carbon number 3, so that's going to be sp3 hybridization. We have a linear geometry around carbon number 4. That's going to indicate sp hybridization, right? So we have 2 sigma overlaps and 2 unhybridized p's for the 2 pi bonds that go around the sigma bond, right? That's with a triple bond. Same with number 5 and with carbon number 6. Again, we have 4 bonded pairs, no lone pairs. This is sp3 hybridization. So I did the molecule. Oh, all right. So they wanted with B, right? How many sigma bonds? So the sigma bonds are single bonds. In a double bond, it's 1 part sigma bond, 1 part pi overlap. And with a triple bond, it's 1 part sigma bond, 2 parts pi overlap. So I have 13 sigma bonds and 3 pi bonds in this molecule. You have 120-degree bond angles with a planar trigonal geometry. That's going to be around carbon 1 and 2. And like I was trying to say before, I tried to make a 3D rendering of this molecule, right? So you can see the 120-degree bond angle around carbon number 1. So again, this indicates sp2 hybridization. 120 around carbon number 2, 109.5 around carbon number 3, 180 around carbon number 4, 180 around carbon number 5, and 109.5 around carbon number 6. So a planar trigonal geometry is an indicator of sp2 hybridization. And anytime you have a double bond, you need unhybridized p to get that pi overlap. So a double bond, you automatically have an unhybridized p, so it's either sp2 hybridization or sp. You need unhybridized p's for double bonding or triple bonding. So sp2 hybridization around carbon number 2. Four bonded pairs, no double bonds. That's going to be sp3 hybridization around carbon number 3. 180-degree bond angle, right? A linear geometry around carbon number 4. Again, we need 2 unhybridized p's for that triple bond. So a triple bond is 1 part single bond, 2 part pi bond. Same around carbon number 5. And tetrahedral geometry around carbon number 6. So sp3 hybridization.